In this video lecture, we will go through tubular reactors now. And just to remind you, we are doing chapter isothermal design reactors. Isothermal conditions means temperature is constant, right? And the value of reaction rate constant, K would be constant, right? So wherever we have K in coming derivations, it is considered as constant because temperature is constant, right? We have done we have done design equation for tubular reactors, right? In previous chapters, we derived design equation for for tubular reactors from mole balance equation, right? Then in the third chapter, we have looked into the rate law, right? And your stoichiometric tables, right? So in this chapter, we would be taking everything together, right? That is mole balance, rate law, and stoichiometry, and we will build the stoichiometry, the design equation for tubular reactors, right? Tubular reactors, we have discussed this before also in chapter 2, that chapter 2 and chapter 1, that these reactors are mainly used for gas phase reactions, and we will consider the flow, right, in the tubular reactors as plug flow, right? By saying plug flow, we mean that the velocity in fluid dynamics, plug flow means that the velocity of the fluid in any of the cross section, right, of the reactor will remain same, right? And there are no radial gradients, right, in temperature, velocity, and concentration. Let me just draw the diagram, and I hope you remember we've done this diagram before. This is how tubular flow reactor looks like. Right, from one end we feed reactants, right, and from the other end comes product, right? And there are some assumptions that we take here. First is, remember, mainly gas phase reactions are done, but in this lecture we would be looking into liquid phase reactions and gas phase reactions. Mainly this is a flow reactor, so anything that can flow, we know that gases and liquids can flow, so gaseous and liquid reactions are done in plug flow reactors or tubular reactors, right? So mainly gas phase reactions and liquid phase reactions, right, are done here. And we assume that we assume the flow as plug flow, right? And plug flow means velocity will be same in any of the cross sections of this reactor. You check it over here in this cross section, velocity will remain same, right? As it is flowing, as the liquid is flowing, fluid is flowing in forward direction, right? And the flow is plug flow, and it also means there are no radial gradients. There are no gradients radially, right? With respect to temperature, velocity, and your concentration, right? So this is a plug flow reactor and no radial gradients. When we say radial gradients, suppose there are no variations. When we say radial gradients, it means there are no variations in temperature, concentration, and velocity radially. That is, if I look here along this radius, right, along this radius, let me show you with a different color. Like this, along this in radial direction, these three things, temperature, concentration, velocity, will remain same, right? This is what we assume, and right, and as we progress in this subject, right, chemical reaction engineering, we would be looking into different scenarios when there would be radial gradients, right? We'll do that in future lectures, in future chapters, right? So these are two things: gas phase reactions, right? And the other thing is your plug flow, right? And no radial gradients, right? And Third important thing is we know that as the reactants move in the forward direction, what is happening basically in this plug flow reactor is reaction is taking place. Since reaction is taking place, so that means reactants are getting consumed, right? So the concentration of reactants in this direction, in the axial direction, will decrease, right? So as the reaction progresses or as the time progresses, the concentration of reactants will go down in in this direction in which liquid is flowing or gas is flowing, right, in this direction. So concentration will of reactants will decrease. Down arrow means it's decreasing this direction, right? Now, if you remember, we have derived a differential form of design equation and an integral form of design equations from mole balance, right? In previous lectures. Right? You can look at the design equation for flow reactors. I have a lecture. It is in the complete playlist. You can look at the previous lectures. You would be able to see if you have any doubts related to the design equation, right? How to derive design equation from mole balance equation. I have all the lectures there, right? But for this lecture, you should know how to develop or how to make the stoichiometric table for flow reactors with variable volume, right? Because it's a little tricky derivation that we have done in chapter 7, chapter 3rd, I'm sorry, right? So two lectures I would recommend here. This first is batch reactors with variable volume. Then the most important is for this lecture is your plug flow your flow reactors with variable volume. Right? You should go through those lectures if you are not familiar with the derivations that we've done there. So two form of design equations that we developed. First is the differential form. Right? Differential form was FA0 dx upon dv is equals to minus RA. Right? We derived this from mole balance equation. We have done this in chapter 7. Right? And this equation, the differential form of design equation is used. This is used when there is pressure drop in the reactor. Right? When there is pressure drop in the reactor. How can the pressure drop takes place? Because if you look at any chemical reaction, if the number of moles are going down, right, that is, if volume is going down, right, then the pressure will go down. So there can be a condition when your pressure will go down inside the tubular reactor. Right, so this design equation is used in case of pressure drop. The other design equation that or the pressure drop, and the second is if there is heat exchange. If there is heat exchange between this flow reactor, and if there is heat exchange, right, between this flow reactor and the surrounding, right, then we will use this differential form of the equation, right? Now let's the other equation that was your integral form, right? Integral form was V is equals to, V stands for the volume of this reactor, plug flow reactor. FA0 we have used in the above differential form also. FA0 stands for molar flow rate, right? When we say molar flow rate, we mean the number of moles passing through any point, say at this point, right? Number of moles passing through this point at any time t, right, is your molar flow rate. How many moles are flowing through this point at any time t is molar flow rate, and how much volume is flowing through this point at any time t is your volumetric flow rate. Right? So you should be aware of this, right? Because we would be using here in case of plug flow reactors, the concentration that we use, right, is your FA0 moles, which is your moles divided by mole. We know that concentration is moles per unit volume, right? Moles per unit volume. So when we talk about plug flow reactor or flow reactor, we are considering the number of moles passing through one point, passing through a point, which would be molar flow rate. So in place of number of moles, we have FA0, which is molar flow rate. It's nothing but moles. So nu zero, right? Volumetric flow rate. How much, what is the rate of volume passing through this point, right? Volume flowing through this point. So V is equals to FA0, 0 to x. X stands for conversion. Then you have dx upon minus RA. This is your integral form. This is your, since we have an integration sign, so this is an integral form of design equation, right? And this equation is used when there is no, this is used when there is no pressure drop. For now, just remember this, right? So these are two important design equation for tubular reactors, right? And one differential form would be used in case of pressure drop or heat exchange, and the integral form would be used in case of no pressure drop, right? No pressure drop or no heat exchange. Right. Now let's consider a reaction where A, reactant A, which is, I'm sorry, in this tubular reactor, is changing into products. This is changing into products. Right now, if I want to, now since in this chapter, what we are doing is we are looking into design equation, rate law, and stoichiometry together, right? We would be using all these three things together to develop the design equations, right? So for this reaction, the rate law would be minus RA is equal to C, I'm sorry, first K, which is reaction rate constant. And since this is an isothermal reaction, it will remain constant. Right, so K would be constant. Ca is your concentration at any time t along the length of this reactor. Right. Now we will consider two scenarios. We will first look for the liquid phase reaction and then we'll look for a gas phase reaction. We are looking into the liquid phase reaction where the volumetric flow rate, right, would be same, right? Nu is equals to nu zero. Right, now let's quickly look at the design equation. The first equation, you will use this equation first, right? And as per, in place of RA, this is first equation. This is your, say, second equation. So we'll substitute RA is equals to KCA square in equation first. What we will get is FA0 dx upon dV is equal to KCA square. Right, we'll just quickly rearrange this equation, right? And we will, what we get is dx upon dV is equals to KCA square divided by FA0. Right, this is your molar flow rate. Right, and from stoichiometry, right, from stoichiometry, we know that stoichiometry, or when we define concentration, we've done this in previous lectures, defining concentration in terms of conversion X, right? So concentration at any time T would be equal to initial concentration minus how much have reacted. right? You know that concentration X. I hope by now you know what is concentration and its formula. Concentration is equal to your how much have reacted, right? And how much you have initially fed, right? Initially fed is Ca0, and how much have reacted, let's say Ca, or, right? Or whatever, how much have reacted. So how much have reacted would be how much have reacted would be XCA0, right? So what is remaining? If this much have reacted, initially you have taken Ca0, so how much is remaining would be Ca. What would be Ca? Ca would be initial minus how much have reacted, because what have reacted has gone, right? So remaining would be Ca0 minus reacted, which is Ca0 dot x equal to Ca0 1 minus x, right? This is this is defining concentration in terms of conversion. Now what we will do is we will substitute Ca in this equation, right? In equation third to further solve this equation, right? So what we will get is dx upon dv is equal to Ca, right? So when you will substitute Ca in this equation, it will become Ca0 square 1 minus x whole square, right? Divided by Fa0, right? And Fa is equal to, we know that Fa can be calculated from this formula for Fa is this molar flow rate divided by volumetric flow rate, right? We'll substitute that as well, right? So let's rearrange this equation, right? On rearranging this equation, what you will get is V is equal to rearranging and then integrating, right? What we are doing is rearranging and integrating, right? This equation. So you take this dV there and Fa above, then Ca comes down. What it will become is equation like this: Fa0 divided by K Ca0 square, right? Since we are, I said we are integrating, so when you integrate dV, it will become V. Then you integrate this 0 to x, right? Conversion. Then you have dx, this dx divided by, when this will come down, it will be 1 minus x whole square, right? So now you have to solve this integral, right? So when you solve this integral, right, what you will get is, and you can substitute for Fa0 also. Fa0 would be from this formula, it would be Ca0 dot nu 0, right? So it will become, when you put here Ca0 dot nu 0 divided by k Ca0 square, right? And when you solve this integral, you will get x minus 1 minus x, right? So one c would cancel out, so it will become nu about divided by, the equation will become, this will become nu divided by k Ca0, I'm sorry, there is no integral sign, we have solved the integral, will become x divided by 1 minus x. This is simple, these are simple calculations. So what we got is, this is the expression for, this is the expression for the volume, right? Volume of this flow reactor, right? Or volume of this tubular reactor. Now we would be introducing another thing, space-time, right? Space-time we have done in chapter 2. Space-time is the time that a fluid take, right, to completely enter the reactor, right? And we also said that in the lecture on space time and space velocity, that space time is one of the performance measure of flow reactors, right? And lesser is the space time, higher is the performance, right? That is quickly it's processing the feeds, the reactants, right? And its formula is volume of the reactor divided by the volumetric flow rate, right? So, right. So we have equation that we derived is V is equals to FA0. I'm sorry, this we have done. So volume of the reactor is equals to nu zero volumetric flow rate K, which is constant, Ca0, right? X upon 1 minus x upon 1 minus x. This is the equation for the volume of the reactor, right? And one thing, this Fa0 upon K, Ca0 square, we have taken out of the integral. Why? Because we know Fa0 is constant. Since conditions are isothermal, so K is constant. This is the initial concentration, which is constant, right? So this is out of the integral, right? Now, space-time. Space-time represented by this letter, tau, Greek letter, right, is your volume of the reactor divided by volumetric flow rate, right? And this is the time taken by the fluid to completely enter the reactor, right? And is one of the performance measure, performance measurement parameter of the flow reactors, right? So now we will find tau. How we'll find it? Space time will divide volume, this volume, with nu zero. So what you will get is 1 upon K Ca0 x upon 1 minus x, right? And when you further solve this equation, right, you get conversion x is tau K Ca0 divided by 1 plus tau K Ca0, right? And we have done in previous video lecture that tau K is your Kohler number, right? Tau K is your, sorry, the product of space time and reaction constant, right? Tau K is your dA. I'll use 2 here because this is Kohler number for second order reaction, right? If you remember, the rate law that we have used in the beginning was RA is equals to, this is what we have used, RK is equals to Ca square, which is the second order reaction, right? So Kohler number for second order reaction is this, right? Tau K is your Kohler number. So what we, then this equation will become dA2 Ca0 divided by 1 plus dA2, right? I'm sorry, there is no, it's not there, right? So XA, X is equals to, in terms of Kohler number, it's dA2 divided by 1 plus dA, right? This is the equation, right? If you just recall, we have already done this Kohler number in the previous lecture, right? Now, so this is the equation for liquid phase reaction, right? Now, the second that we would be looking into is the gas phase reactions, right? So this is your Dam-Kohler number. I'm sorry, one thing I've missed here. This is the Dam-Kohler number for first order reaction, right? And Dam-Kohler number for second order reaction is tau K Ca0. It would be Da2. This is the Dam-Kohler number for second order reaction, right? So this equation changes to this form. In place of tau K Ca0, this is Dam-Kohler number for second order reaction. This is the equation, right? Now we will consider a gas phase reaction. Right, I hope this is clear. This is a simple derivation, and most of the things we have already done. Right, now we will consider a gas phase reaction. Let's quickly look at the gas phase reaction. We would be using stoichiometry. It's important to look at the stoichiometry that we have developed in variable volume plug flow reactors, or variable volume, sorry, flow reactors, right? Because if you remember, there we have derived, we have reached at one relation where epsilon is equals to your delta, right? Then YA0, right? We would be using this relation. This is increase in the number of moles, right? So you should know this. You should know from where we got this, right? And this D is equals to D upon A, right? Plus C upon A minus B upon A minus 1, right? And YA0 is your mole fraction of A, mole fraction of A. You should know all this to understand what we are doing now. So gas phase reaction, right? Gas phase reaction at constant temperature and constant pressure, right? At constant temperature and constant pressure, that is T is equals to T0 and P is equals to P0, right? Concentration is expressed. Now we will derive concentration in terms of conversion X by using the formula that we did a moment before, minutes before. It would be FA. Now this nu is equals to nu 0 1 plus epsilon X. This we have derived in flow reactor when we did derivation for flow reactors, or for variable volume flow reactors, right? You have to then look into that derivation to understand how we reached here. And epsilon is the product of delta, which is increase in volume and mole fraction, right? And epsilon is this increase in the number of moles, right? That's what I was talking about. That's why I told you these some formulas. Nu is equals to nu 0 1 plus epsilon X. X is your conversion, right? Now this will become an FA for flow reactors, right? We have derived that FA is equals to, like we did for concentration, CA is equals to CA0 C1 minus X. So similarly, FA is equals to FA0 1 minus X divided by nu 0 1 plus epsilon X, right? So it will become CA is equals to CA0 1 minus X divided by 1 plus epsilon X, right? Now we will solve this further, right? Using the rate law equation. Rate law equation is your minus RA is equals to KCA square, right? So now we will combine stoichiometry, rate law, and your mole balance equation for flow reactors, right? So it will change into, and we are using here this equation. We would be using this equation, right? Integral form of equation, right? An integral form of equation was v is equals to, integral form of equation was v is equal to fa0 integral of 0 to x dx upon minus ra, right? So in place of ra we will put kca square, right? Then in place of ca square we will put this, right? So after solving, what we will get is, then we will integrate, right? V is equals to fa0, this is constant, it will come out of the integral, 0 to x, right? 1 plus epsilon x whole square upon 1 minus x whole square dx, right? And you have kca0 square, this will come out, right? And eventually it will come out of the integral because this kca0 is also constant, right? So it will develop like this, fa0 divided by kca0 square 1 minus x square. I'm sorry. I have to take this out, right? It will become v is equals to fa0. We'll take this out. K is equals to ca0 square, right? Then integral 0 to x 1 plus epsilon x square divided by 1 minus x whole square dx, right? This is the equation. Now you have to solve this integral, right? So once you solve this integral, what you will get is, right? We are not solving it here, right? This is how it's given in your book, that after solving, if you want, you can solve it, right? And see if you get this. I did this and we do get this, right? Epsilon 1 plus epsilon logarithm of 1 minus x, right? Plus epsilon square x plus 1 plus epsilon square x divided by 1 minus x, right? This is what you will get, right, after solving that integral. Now here we have defined volume in terms of conversion, right? And epsilon, I'll again write it over here, is del into y is, right? And del is your, now we would be doing a little graph to understand more on this, right? And epsilon is your, the value of epsilon is, I've written in the previous page, it was d upon a, right? We have done this. This is very easy to conclude. It's minus c upon a minus b upon a minus 1, right? Sorry, this is wrong. D upon a plus your c upon a minus b upon a. This is your increase in the number of moles, right? And ya0 is your mole fraction of reactant a0, right? Or reactant a, and this is for reaction. This is for reaction A plus B upon A. B gives you C upon A, C, right? Plus D upon A. It's for this reaction, right? Epsilon, right? Epsilon is for this reaction. So just for your understanding, what we have done in the previous lecture, right? Now, using this equation, Like this equation, using this equation, we will draw a graph, a plot of conversion along length, right? Length is the length of the reactor, right? That is volume, right? We will plot a graph between volume and conversion x, right? What we have is the relation between volume of the reactor and conversion, right? So we will be drawing a graph like this. This is what you see in the Fogler, in your Fogler book, right? Conversion is taken on x-axis, right? And volume is taken on y-axis, right? And this kind of, you get these kind of graphs, right? For particular values of epsilon, right? This is the kind of graph that you see, right? Now let's discuss this graph, right? So plot of conversion along the length, right? Length of the reactor is shown for 4 reactions, right? Each of this line corresponds to 4 different reactions, right? And value of epsilon are given for the same value, and we know that in the integral form, because we are drawing this graph based on this equation, nu upon k c a 0, this is your constant, right? So now what we basically want to look is the effect of change in the number of moles in the gas phase on the relationship between conversion and volume, right? How change in when a reaction is taking place, right? Say this reaction where you have 2 moles of A are changing into 1 mole of B. That is, there is decrease in the number of moles, right? Similarly, if you have A, which is changing into 2B, where we have increase in the number of moles. The third scenario is A is changing into B, there is no change in the number of moles. How will this change in the number of moles? Because in any of the gaseous reactions or liquid reactions, we would be having one of these conditions. Either number of moles will increase, decrease, or will remain same, right? So based on this, we will find the value of epsilon, right? You have epsilon here, and epsilon is del y0, and del is your change in the number of moles. So change in the number of moles, right? We would be considering 3 scenarios, right? When change in the number of moles is 0, right? That is when there is no change, A is changing into B. When change in the number of, let me just highlight it with a different color, right? When there is no change in the number of moles, delta is equals to 0. When there is increase in the number of moles, right? When number of moles will increase, then your delta, for this case, delta will go down and epsilon will also go down, less than 0, right? And the other scenario is when there is no change. In the case of no change, like in this case, you have delta is equals to 0 and epsilon is also equal to 0, right? When there is decrease in the number of moles, right? Like here in the first case, I'm sorry, I've written it over here. When there is decrease in the number of moles, you have delta is equal to less than 0 and epsilon is less than 0, right? When there is increase in the number of moles, then you have delta is greater than 0, then epsilon is greater than 0. These are the three things that we would be looking into, right? And based on the increase or decrease in the number of moles, we will be looking into the flow rate, the volumetric flow rate, right? So let's look at it. We have derived one equation in the flow reactors using gas equation, if you remember in the previous lectures, right? I'll just write it over here. You can refer to that lecture in flow reactors with variable volume, right? We used gas equation, which was PV is equals to NZRT, right? And we used F is concentration is equals to FA0 divided by mu 0, right? Using these equations, we reached at this relation where with for flow rate, mu is equals to mu 0, 1 plus epsilon x. You have to look previous lecture for this formula, right? Now, based on the value of epsilon, right, we would be looking into the flow rate, right? Flow rate of the reactants will increase, decrease, or remain the same, right? If the flow rate will increase, then reactants will have less time. Reactants will stay in the reactor for less time, right? If flow rate will increase. Let me just show you. If this is the reactor, right? If volumetric flow rate say go down, if the flow rate goes down, then reactants will spend more time in the reactor. If volumetric flow rate will increase, then reactants will spend less time in the reactor. Right? Less time means they will flow quickly out of the reactor, and they will react for less time inside the reactor. If they react for less time inside the reactor, that means conversion is less, right? Whereas if volumetric flow rate will decrease, reactants will stay for a longer time inside the reactor, hence conversion will be high, right? That's what we would be looking into using these equations and the value of epsilon. Value of epsilon, as I already said, is your delta y is 0, right? And delta is this increase in the number of or change in the number of moles. So first condition is when for reaction A is greater than, I'm sorry, A gives you B. When A gives you B, that means there is no change in the number of moles. Delta is equals to 0. If delta is equals to 0, then if I put the value here, delta is equals to 0 means epsilon is equals to 0. Right? If I put this value here, then nu is equals to, nu would be equal to nu 0. Right? Because epsilon is 0, so nu is nu 0. That means fluid moves through the reactor at constant volumetric flow rate. Right? Fluid moves at constant volumetric flow rate, right? As the conversion increases, and since fluid is flowing at constant volumetric flow rate, so conversion is increasing as the conversion increases. So basically, we are looking at conversion, right? Based on the change in the number of, based on the reaction. And does the reaction result in the increase in the number of moles, decrease in the number of moles, or the number of moles remains the same? Right? The first case is when the number of moles will remain the same. Right? So fluid moves at constant volumetric flow rate, right here. Now let's take the second scenario. In the second scenario, when there is decrease in the number of moles, that is this kind of reaction. 2A gives you B. Here you can see 2 moles are changing into 1 mole. That is, there is decrease in the number of moles. Right? For decrease in the number of moles, we have delta is less than 0. If delta is less than 0, right, then epsilon, if delta is less than 0, right? Then epsilon will also be less than 0, right? It can be easily seen. Epsilon will also be less than 0. Then this relation will kind of become mu is equal to mu 0 1 minus 0.5x, right? 1 mu is equals to mu 0 1 minus 0.5x, right? So the volumetric gas flow rate will decrease. That is nu. If you substitute this here, since epsilon is less than 0, so nu would again be less than 0, right? That is volumetric flow rate will decrease, right? This is important. Volumetric gas flow rate decreases as the conversion increases. Here, volumetric flow rate decreases. So when flow rate decreases, that means it's flowing with a lesser speed, right? That means reactants will spend more time inside the tubular reactor. When they spend more time, that means conversion will increase, right? So when there is decrease in the number of moles, conversion will increase, right? Now let's take the third scenario where there is increase in the number of moles. Right? When there is increase in the number of moles, we have delta greater than 0, epsilon is also greater than 0, right? Then this expression, as per this expression, nu would be greater than nu 0. That means flow rate increases, right? When flow rate increases, what will happen to conversion? Flow rate increases means reactants will quickly cover the length of the reactor or the volume of the reactor, and they will quickly come out from the other end, right? That is, they have less time inside the reactor. So conversion decreases, right? This is important. So this is it, right? So just we have to look at the residence time, right? When your volumetric flow rate increases, that means residence time decreases, right? The reactant would be for a less time inside the reactor, right? Less time means reaction would be less, so conversion will decrease, right? Whereas when the time, right, or when the volumetric flow rate increases, right? So in that case, molecules will spend more time. When the volumetric flow rate decreases, molecules will spend more time inside the reactor along the length of the reactor, right? So there would be more reaction. More reaction means more high conversion, right? This is what you have to understand. And there is a little small graph, right, for what we have just understood. It is somewhat like this. Here you have V, here you have this, right? When nu is equals to nu 0, the graph would be like this, right? And when there was increase in the number of moles for this, when delta is greater than 0, right? It will be like this, right? Because when delta was greater than 0, you look at this, when delta was greater than 0, nu, that is volumetric flow rate, was higher. It was increasing, right? So you can see this, it's on increasing side, right? And when there is decrease in the number of moles, this is the graph that shows decrease in the number of moles, right? When decrease in the number of moles, then this nu would be less than nu 0. That is, This is decreasing, right? And this is for the case when delta is equals to 0, right? And epsilon is equals to 0, right? I hope all this is clear. Epsilon can be here half, less than 0, epsilon is 1, right? Greater than or equal to 0. Right, I hope this is clear. This graph shows change in gas phase, volumetric flow rate down the length of the reactor. Right, we were looking at the flow rate, right, as the reactants are moving down the length of the reactor, as the reactants are moving in this direction. Right, so depending on nu is less than nu 0, greater than nu 0, or equal to nu 0, you have these graphs, right? And based on that, you conclude whether conversion will increase, will decrease, increase, right, or will remain same, right? So this is important, right? From practical side, right? From practical side, this is important. Just try to correlate this with how will you, I mean, look at things, right, when you have practically these kind of scenarios, right? If you just look at the reactor and just try to relate the speed with which reactants are flowing, right? And what would be, and look at the reaction, whether there is increase or decrease in the number of moles, right? So how that increase or decrease in the number of moles will affect the volumetric flow rate, and then finally how will it affect the conversion, right? Looking at all the derivations, because you would be requiring these derivations. Chemical engineer would need all these formulas for their calculations, right? So make sure you understand all these things, specifically in this chapter and what we have done in the third chapter. Right? I hope this is clear to you. Thanks.